Hello and welcome to section 6 of the Mastering Keras course. We're going to be looking at deep reinforcement learning in this section, and actually I think this is one of the most interesting applications of deep learning, and Keras makes it very easy to do, so let's jump into it. We're going to start off, sadly, with a theory-based lecture, but I promise there's going to be lots of interesting code examples to work through in the remainder of this section. Now, we're going to begin just talking about what reinforcement learning is, because it's quite different to standard supervised learning. In reinforcement learning, you're training up a system that's going to take actions in an environment. So it's going to control the environment. It is going to learn which actions to do by obtaining feedback from the environment. The aim, of course, is to get our control system to act in such a way as to maximize the value of the environment to it. And we will get to define the value of the environment, so we want the control system to maximize the value to us. So in this video, we'll look at the basic ideas behind reinforcement learning, including giving a pretty rigorous definition of the problem, and we'll distinguish between model-based and model-free approaches. As I said, there'll be no code component to this video, but there's going to be lots of code in the remainder of this section. Now, to get a really rigorous understanding of what we're trying to do with reinforcement learning, I'd like you to consider a dynamic system. The state of this system, which is being represented by S in this diagram here, evolves over time based on some sort of system dynamics. These system dynamics are governed by what we call the transition function. So the state of the system at the next time point depends on the state of the system at the previous time point, as well as whatever action we do at the previous time point. So given a current state and given some action, the system will evolve, probably stochastically, so probably including randomness, to some new state. At each time point, we also get a reward, which indicates the value to us of the system being in that state. So this is going to be governed by a reward function. Now I say in the diagram that both the transition and emission functions, or reward function, can contain randomness, and typically this will be the case. The aim of the game for us is to discover a high-quality policy, and a policy is a function that returns an action for every state. So basically, our policy will tell us what to do in any given state, and we want to get a high-quality policy that will provide us with plenty of rewards. Now, how are we going to measure the quality of the rewards? We don't want to just look at immediate rewards. If you're near a cliff, the cliff is on your left, and you move to the left, in the very short period of time between moving and falling, you may experience some sort of reward. There might be a fresh breeze, but pretty quickly this is going to be a bad situation. So we don't want immediate rewards. We want policies that will lead to long-term high cumulative rewards. And we're going to define this rigorously by talking in terms of expected cumulative discounted rewards. For shorthand, we'll call this utility. Now, the utility, and you can read these slides over in detail if you're interested in getting to grips with the mathematics here. The utility function is going to measure our expected long-term rewards. So not just the rewards of the next state we turn up at, but the long-term rewards, the sum of all the rewards we can expect by following a particular policy from a particular start state. But we're going to also introduce a discount factor, which is going to privilege short-term rewards over long-term rewards. So the rewards that we expect to occur immediately or near immediately in the short term will be privileged over rewards we expect to occur in the long term by following a particular policy. Now, this can be justified by the sort of reasons that I just said, that we want to prioritize short-term rewards because, for example, they might be more likely to occur than these more uncertain long-term rewards. But actually, mathematically, this becomes really important in allowing our utility function to converge because we're summing over potentially infinite sequences of rewards, and we need convergence. So actually, there's a mathematical reason for wanting this discount factor above and beyond any philosophical reason about privileging short-term rewards over long-term rewards. At any rate, let us continue. Now, if we know the environment, if we know the transition and reward functions, there are various ways to proceed. We can in fact use algorithms such as value and policy iteration to solve the problem for us, to determine the optimal policy to follow to maximize long-term rewards in this environment. When we're in a situation where we do not know the environment, where we do not know the system dynamics or the transition function in particular, we typically know the reward function because we have to specify it, but we're often in a situation where we don't really know how the system evolves over time, what the relationship between subsequent states and current states and actions are. In this situation, we're doing reinforcement learning. In that case, we need to not only discover the right policy, we need to discover the right policy whilst, in some sense, learning about how the environment, how the system behaves. Now, there are two principal ways to go about this. The first is model-based. And in this one, what we're going to do is we're going to have our system, have our agent that we're controlling, interact with the environment so that we can essentially sample via experience instances of how the system does behave, so that we can collect data and use it to build models of the transition function. So we can begin to explicitly model the dynamics of the system we're encountering. Once we have high-quality models of how the system evolves, of the system dynamics, we can of course use these to work with the standard approaches of finding good policies, value iteration or policy iteration. Now, there's some issues about scaling and so forth, but that's the basic idea. However, it might surprise you that we don't actually need to do this. We don't actually need to model the environment, because after all, what we really need is a way to estimate the utility of taking particular actions in particular states. Once we have such a means of estimating the utility of any action in any state, we can use this to decide the policy. We just need to choose the action we think leads to the biggest utility. And we're going to call these expected utility of actions at given states the quality or Q value of the action at the state. If we were doing a model-based approach, we would be estimating these Q values via inference on our models of the environment. But model-free approaches aren't going to do that. They're going to directly estimate Q values for state action inputs. And we're going to focus on model-free approaches in the following videos. So this is what we're going to be working with. If you think that this is odd or surprising, it's actually not. It's an instance of a very common approach. Consider the situation. Let's imagine a simplified world where the salary that you have depends only on the job you hold, and the job you hold depends only on the grades you had at university. Now, there may be some randomness involved in these relationships, but that's the basic causal structure. So if we wanted to model the relationship between your grades at university and your salary, then we could, of course, explicitly model this whole chain. We could model the relationship between grades and jobs, then the relationship between jobs and salary, and work out the relationship between grades and salary by performing inference on this chain. But of course, we could just collect data on grades and salary and model these two directly, model the correlationship between grades and salary while ignoring this intermediate variable of which job you hold. There's still going to be correlations between grades and salary. We don't need to explicitly model the intermediate variable job. And what's going on in the dynamic, in the reinforcement learning case, in the Q learning case, is exactly the same. We want to model the relationship between taking particular actions in particular states and then following a particular policy with expected utility. Now, the actual relationship between following a particular policy and expected utility goes through how the system is going to evolve based on the actions we take. But we can marginalize over that and just directly model the relationship between taking certain actions in certain states and following a particular policy and the expected rewards without explicitly modeling how we expect the system to evolve based on this. So go over these slides a little bit more on your own time if you're interested and if you're having a bit of trouble following these ideas. The point is, we're going to be focusing on model-free approaches. Our aim is just to get quality values for state action pairs. We're going to be seeing how we can obtain high-quality deep learning models of the quality function. So we're going to be using neural networks to estimate Q values for taking particular actions in particular states. And of course, once we have that, we can read our policy off it. For any given state, we're going to choose to do the action that maximizes the expected quality, that we estimate has the highest quality. Now, if that's relatively straightforward, unfortunately, we're going to see that this is quite difficult in practice because there's various forms of instability that are going to plague the process. So we'll look at what these forms of instability are and how we can deal with them. We'll see that in the simple case, we're going to be working with discrete valued actions. And I've already sort of assumed this by saying, look, we can use our quality model to determine our action by just examining which of the actions has the highest quality for this state, and then choosing to do that action. But that only works where there's a finite number of actions. So if we've got real valued actions, this approach is going to fall apart. So we'll also consider how to deal with cases where actions could be real valued rather than discrete choices.